Our project was the Galaxy Morphology project on the Astronomy team. My name is Elizabeth Craig.
I'm Liana Krasnoff.
I'm Catherine Teague.
And I'm Knapp.
So to give you some background about our project, there's a large variety of characteristics possible for different galaxies to have, such as bulges, bars, and disturbances. For our project specifically, our main goals were to classify galaxies according to their shape and characteristics, and then take these classified galaxies and find patterns in the data, and then collaborate with each other to learn more about the evolution and formation of galaxies through our findings. So throughout this presentation, there's going to be some labeled picture representations of what some of the defining attributes we classified galaxies by look like in real life.
This slide shows one of the first slides of some images that we worked with during our Galaxy Zoo classification. So on the far left, we have an elliptical galaxy, which is one of the possibilities we could choose to classify a galaxy as. And then in the middle, we have a spiral galaxy, and that was the other possibility for classifying galaxies. And then on the far right, we have a star or an artifact, which was another thing that we could choose to classify some of the images we were working with as.
Our approach to this project was that each group member classified upwards of 40 galaxies for a total of 180 total galaxies. We discovered if the galaxy was spiral or elliptical and looked at its shape, disturbances, rare features, and surroundings. We then took the data and calculated percentages that correlated with how often we saw a certain feature. As we did this, we noted challenges and worked through them as a group. Finally, we discussed our results and the significance of this project.
In our research, the trend that stood out to us the most was how few spiral galaxies there were compared to the number of elliptical galaxies there were. In fact, out of 180 galaxy classifications, only 22 were spiral galaxies, a mere 12.2%. On the other hand, we found 142 elliptical galaxies, which is around 78.9% of the galaxies we classified. Additionally, we saw 12 disks, making up 6.7% of our data. On rare occasion, we did see a star or artifact, which made up 2.2% of our classifications. Our group discovered a possible cause for this imbalance. Giant elliptical galaxies form from the collision of spiral galaxies, meaning that they are typically older. Since there is evidence the formation of new galaxies is infrequent, this could be a reason why we are seeing so many more elliptical galaxies compared to spiral.
So specifically in terms of elliptical galaxy characteristics, we found that they were mostly an ovular shape, which made up about 45.4% of those that we classified. The next most common was the completely round shape, making up about 37.6% of the ones that we classified. And then finally, there were very few cigar-shaped elliptical galaxies, making up only 17% of those that we classified. And as you can see, there's some pictures on the right. So sometimes it was difficult to tell disks, cigar-shaped galaxies, and edge-on spiral galaxies apart. So we decided to classify disk galaxies in their own category so as not to mistake them for a different type of galaxy. And as you can see on the left, they do look very similar to the cigar-shaped galaxy that we showed in the last slide.
So on the rare occasion that we did classify a spiral galaxy, we found that most didn't have bars in the center. And additionally, about 59.1% of the galaxies had tightly wound arms, whereas only 36.4% had medium wound arms and 4.5% had loosely wound arms. And all of the spiral galaxies that we classified had 1 to 3 arms. Around 55% of these spiral galaxies had a moderately sized bulge in the center, and 45% had a small bulge. And on the left, you can see images of what we mean by tightly wound, medium wound, and loosely wound, and different sizes of bulge in galaxies.
Overall, we found very few disturbances in the galaxies. Disturbed galaxies only made up 17% of our total galaxies classified. When there was a disturbance, it was typically minor, which made up about 60% of all disturbed galaxies. Next was merging galaxies, which made up about 26.7% of disturbances. Finally, there were fewest major disturbances, only making up 13.3% of our total galaxies classified.
Similarly, there were almost no rare features, only affecting 11 galaxies. We most commonly saw overlapping galaxies, which made up 63.6% of rare features in galaxies. Next, we saw two rings on galaxies, making up 18.2% of rare features. And finally, we saw two irregular galaxies, making up 18.2% of our total as well.
This project allowed us to grasp a greater understanding of galactic evolution, giving us clues as to what galaxies, including our home galaxy, the Milky Way, could eventually look like. This information also helps to provide context and visualization to some questions that have not been answered yet, simply because we have not observed long enough. We also came to understand how rare spiral galaxies were compared to elliptical galaxies in the data found, and even rarer were special features and disturbances, giving to hints as to what the conditions had to have been for these rare features to occur. Spiral galaxies are in many cases younger than elliptical galaxies, which are formed by two spiral galaxies colliding. But just note that distance was not part of the data we were given to work off of, and therefore we could not tell if these elliptical galaxies were a dwarf or a giant. And these are not always younger than spiral galaxies, so they don't apply in all cases. In general, from what researchers have observed, spiral galaxies are identified more often than elliptical galaxies, while elliptical galaxies are estimated to be the most abundant type in the universe. One reason for this could be that spiral galaxies are typically easier to spot since they're brighter. And elliptical galaxies have less gas and dust, giving way to less bright stars, causing them to be dimmer, which is why we don't see as many usually.
Some of the features and challenges of SEAS, specifically the challenges, were that most of us found that we had little prior knowledge or experience in astronomy when beginning this internship. In addition, the astronomy activities were very challenging, but it was very rewarding when we completed them. And sometimes we found that we were unsure of our own skills when we were surrounded by students who we felt were smarter and or more accomplished than us, making us feel a little bit of imposter syndrome. In addition, due to it being virtual, there was more independence in the program, which was a plus, but it also meant that we had to figure out some of the more difficult parts of this program by ourselves with less guidance. In addition, the time restrictions limited the amount of data that we could collect as a group, causing us a smaller sample size, which could cause a less accurate data collection. Additionally, the images of galaxies we classified on Galaxy Zoo were sometimes somewhat blurry, so it was hard to distinguish some of the individual features, which could cause less accurate data collection again. Some of the features of SEAS were that collaboration was a very key aspect. We all had to learn to not be scared to ask questions in general, but also specifically in the virtual environment, and we had to adapt to working with others virtually through Zoom. In addition, we also received extra information and fascinating equipment for being a part of the SEAS program, including a spectroscope, diffraction grading, and a book called The Last Stargazers that described astronomy as a career. In addition, there were live and informative speaker series talks ranging from discussions about careers, internships in colleges, and talking with scientists from many different concentrations across the whole board.
SEAS was tremendously helpful to us for exploring a career in astronomy. It provided us with very experienced mentors that served as role models to us throughout our years. Experiences prepare us for being later in life. We were given the ability to collaborate and got connections with like-minded peers and mentors. We learned all about the careers that organizations such as NASA has to offer. We got to listen to scientists speak from all areas of astronomy, including astronauts. Some of these concentrations include astrobiology, astromaterials, and scientists and engineers talking about space missions. Finally, we received information about NASA internship opportunities, careers, and even about the University of Texas's programs for aerospace engineering and astronomy.
Lastly, we wanted to close out with some thanks. Thank you for your time during our presentation. Thank you to our mentors during this project. Mr. Johnson especially counseled us through this project, but also gave us the independence we needed to become better thinkers and leaders. We have all learned so much with their help, and we are beyond grateful for this opportunity. We wanted to thank Ms. Liana and Ms. Margaret, who did a fantastic job coordinating the program. And finally, thank you to the National Aeronautics and Space Administration, the Texas Space Grant Consortium, the University of Texas Center for Space Research, the Zooniverse, which was essential to our studies, and the SEAS program. Participating in this program has been a surreal and fantastic experience that will stay with us throughout our lives. Thank you.